Last topic of chapter 26 is to introduce some properties of conductors in static equilibrium, and we were already introduced to several properties of conductors in static equilibrium in an earlier chapter, so we'll be adding to that list here. And so far what we've been introduced to are the ideas listed on this slide. One is that any excess charge on a conductor in static equilibrium will be on the surface of that conductor, and that's illustrated with this image of a conducting sphere where the excess charge has moved to the surface of the sphere, and that will be true for any conductor of any shape in static equilibrium. A second property of conductors that we've been introduced to is that, again, for a conductor in static equilibrium, the electric field will be zero inside. And then a third is that the electric field outside the conductor is going to be perpendicular to the surface at every point. And so here the electric field emanates away from the conductor because there's excess positive charge on its surface, and at every point the electric field makes an angle of 90 degrees with the surface. So for this particular conducting sphere, a graph of E as a function of radial distance from the center of the sphere would look like what's shown here, where the electric field is zero inside of the sphere up until the point that we reach the radius of the sphere, and then outside the sphere the electric field will be falling proportional to 1 over radial distance squared. There's another property now that we can introduce for conductors, which is that since E is equal to 0 inside a conductor, the potential will be constant inside a conductor. That is, between any 2 points inside of the conductor. So if we had a point I and then a point F, the potential difference between I and F is going to be equal to 0, and that implies that the potential is equal to a constant as long as we're inside of the conductor. And a proof of this is that for any path we could consider between points I and F within the conductor, when we evaluate the path integral to find delta V is equal to the potential at the final position minus the initial, we would find that the electric field is 0, and therefore the change in potential must be 0. So the entire conductor then is at 1 potential. And this can lead to an understanding then of what we expect a graph of potential versus radial position to look like. So on the left is electric field versus radial position. On the right, what we would find is that outside of the conducting sphere, the potential is going to be that of a point charge, kq over r, just as the electric field is that of a point charge outside of the conductor, as we would be able to prove from Gauss's law. And then inside the conductor, the potential is constant, and the potential will be constant and equal to the value that it will have on the outside just at the radius, the outer radius of the conductor. So at r, little r is equal to big R, we expect continuity, and if it's kq over little r outside, then right at the radius of the sphere, it's going to be kq over big R, substituting in little r equals big R, where r is the radius of the sphere. And then since the potential is constant inside, it's going to be all throughout equal to kq over r. This formula then would allow us to calculate the potential associated with a conducting sphere at all points within the sphere. But the bigger idea is that the potential is constant inside of a conductor, so it's all the same. Okay, and this is an idea that we can use when we're solving problems. This is problem 49 from chapter 26. And in this problem, it says that we have two metal spheres. We have metal sphere 1, which has a positive charge of 6 nanocoulombs. So I'll write Q1 is equal to 6 nanocoulombs, which is 6 times 10 to the minus 9 coulombs. And metal sphere 2 is initially uncharged. So actually, I'm going to put a naught after these charges then to indicate that they're the charges of the spheres in the initial state. Q2 naught for the second sphere is 0 because it's neutral. So these are the charges in the initial state. And then it says the spheres are then connected together by a long, thin metal wire. What are the final charges on each sphere? So what we're trying to figure out is the final charges, Q1F and Q2F. And what we know is that metal sphere 2 has twice the diameter of sphere 1. So in other words, if the radius of the first sphere is r, then the radius of the second sphere must be 2r. And then that helps me draw a picture. So I've got sphere 1 and sphere 2. Sphere 2 is twice as big radially than sphere 1. And sphere 1 initially has a positive charge, and we know that will be distributed over its surface, and sphere 2 is initially neutral. So this would be the initial state before they've been connected together. And then in the final state, we've now connected the two spheres together. And what happens when we do that is that some of the excess charge on sphere 1 is going to be muted by charge flowing from sphere 2 until they're in equilibrium. So we're going to connect these two by a thin rod or thin wire. And the reason for the thinness is so that we don't have to worry about the thin wire playing a role when we determine how much charge exists on the two spheres. We'll assume the amount of charge on the wire is negligible in the end. And so some of the excess charge now is shared by the bigger sphere, sphere 2. And the radius of sphere 2 is R2, which is 2r. Radius of sphere 1 is R1, and that's the same in the final state. Okay, and the question is, now that they are back in equilibrium again in the final state after this initial flow of charge to achieve a balance, how much charge will reside on sphere 1 and how much charge will reside on sphere 2? And the condition that we make use of to solve this problem is that for conductors in equilibrium, the potential of sphere 1 is going to be equal to the potential of sphere 2, because once we connect the two spheres together, it becomes one big conductor. And for one conductor in equilibrium, the potential will be the same throughout. So then that tells me the potential over at sphere 1 must be the same as the potential at sphere 2 in the final state. And then the potential for a sphere is going to be K times the charge on the sphere over the radial distance. And so at the surface, the potential of sphere 1 will be KQ1 over R1. and the potential for sphere 2 will be KQ2 over R2, and this will be Q1F and Q2F. And then I can do some cancellation from side to side, and I can also substitute in what we know for R1 and R2. So I'll move to the next page. So we have KQ1F over R1 is equal to KQ2F over R2, and R2 is equal to 2R, and R1 is equal to R. And then canceling the R's and K's from side to side, we'd have Q1F is equal to Q2F over 2. So in other words, after the charge transfer, we expect half the charge on the small sphere as is on the big sphere. And this is the first equation that we can make use of. The second equation we can make use of is charge conservation. So now we have to look at how much charge was on the system initially, and that total charge would be Q1 naught plus Q2 naught, but Q2 naught was 0. The second sphere was initially neutral. That must be equal to Q1F plus Q2F, and this equation becomes our second equation to find what we're looking for. What we can do in these two equations, we have two unknowns, Q1F and Q2F, and they appear in both equations. So we can use a process of substitution then to substitute from one equation to the other to eliminate one of the two unknowns. So we'll substitute 1 into 2, and that'll give us Q1 naught is equal to Q2F over 2 plus Q2F. And then Q2F over 2 plus Q2F will be 3/2 Q2F, or in other words, Q2F, the final charge on the second sphere, will be 2/3 of the charge on the sphere 1 initially. So this will be 2/3 of 6 nanocoulombs, which is equal to 4 nanocoulombs. And that's the charge on the second sphere after we connect the two conductors. And then Q1F will be the remainder of charge, which will be, if I use equation 2, I'd have Q1F is equal to the total charge available, Q1 naught, minus Q2F, which will give us 6 minus 4 nanocoulombs, which is 2 nanocoulombs. So after we connect the two spheres, charge is transferred from the more populated sphere, which is sphere 1 with excess charge. Some of that excess charge is going to move on to sphere 2. It wants to spread out, and the proportionality of charge on the two spheres when it reaches equilibrium again will be 2 to 1. There'll be 4 nanocoulombs on the larger sphere and 2 nanocoulombs on the smaller sphere. Okay, so that's the idea, the first idea that I wanted to introduce in this chapter, which is that the potential is constant in a conductor. And the second idea that's introduced in this chapter, another property of conductors in equilibrium, is related to how the surface charge density distributes on a conductor. What we'll find is that there's more surface charge, a greater surface charge density at sharp points than there is at more rounded surfaces. And a proof of that is what is shown in this slide. So if we know that the potential on this conducting sphere shown in the illustration is KQ over R, this formula can be rearranged to solve for Q in terms of the potential. And then the surface charge density, eta, which would be the surface charge density on the sphere, that's charge over area, is going to be equal to, if we substitute in our formula for Q, into this equation, then we arrive at the next equation in the series. And then we're also substituting in a is equal to 4 pi r squared for a sphere. One of the r's will cancel from top to bottom, and the equation we arrive at for surface charge density is that for a given potential, so say the sphere is charged to 5 volts, for a given potential V, then we divide by k 4 pi, the radius of the sphere, and that will tell us the surface charge density on the sphere. And what we notice from this expression is that for a given potential, if that stays constant, then the surface charge density is proportional to 1 over the radius of the sphere. So if r goes up, eta goes down, and vice versa. So if r goes down, then the surface charge density goes up. This idea is derived here for a single sphere, but it applies for even arbitrarily shaped objects where if the radius of curvature goes down, then the surface charge density will go up for a given potential that applies over that surface. So this is an arbitrarily shaped object, a good conductor. Inside in static equilibrium, E is equal to 0 and V is equal to a constant. Whatever voltage it has that voltage throughout. And the surface charge density is going to be larger at points where the radius of curvature is smaller. So up here, the radius of curvature is smaller than in this section, where the radius of curvature is larger. So as r goes down, eta goes up. And eta is a factor that we know from the Gauss's law chapter plays a role in determining the electric field strength. So where eta goes up, the electric field at the surface will also go up. And so where we see the charge bunched up is near the sharp points, and the electric field is going to be strong near those sharp points. And this is something I'm going to illustrate with a demonstration using what's called a Van de Graaff generator. And the demonstration, I'm going to first show some general aspects or general party tricks sort of that you can do with a Van de Graaff machine. And then I'll illustrate the application here to create a lightning rod with a sharp point to illustrate how that sharp point affects the behavior of the charge distribution and the electric field near the point. And what a Van de Graaff generator is, and some of you may have seen this in science museums or in one of your science classes, is it's a machine that has a spherical metal dome on top, and that dome will hold a relatively large charge when it's charged through the use of a power supply and a belt. So this sketch on the right is trying to show the inner mechanisms of the Van de Graaff machine. There's a power supply at the base with a metal brush, and charge is transferred from the metal brush to the belt, and then the belt rotates in the machine and will carry that charge to the top inside of the dome. And then there's another metal brush that will transfer charge from the belt off to the dome, where it then spreads out over the spherical surface. And the manufacturer of the Van de Graaff device that I'm going to demonstrate says that it has the potential of holding a charge on the dome Q, which is equal to 2 microcoulombs. That may be a little high. Our Van de Graaff is a little older, although I did just put a new belt on it. But let's say that it actually holds 2 microcoulombs when it's fully charged. Then we can calculate what the potential is going to be, what the voltage is on the dome, using KQ over R. And the radius of our Van de Graaff, R, is 10 centimeters. So if you plug in the K, Q, and R values, you can calculate the voltage on the dome, and it works out to be 1.8 times 10 to the 5 volts, or 180 kilovolts, which is a pretty impressive voltage. And so that's what I'm going to demonstrate the effect of. Just for comparison, the voltage that comes out of your wall outlet is 120 volts RMS, or 170 peak voltage. It's an AC voltage, so it's a little different, but it's nowhere near this 180 kilovolts. And yet, I don't have to be terribly afraid. If I accidentally touch the dome, I will get a shock, and it will be painful. I've had that happen before, but it's not going to be anything too serious. And the reason is because there is a limited amount of charge available to transfer, and so the current is very small. And once that little bit of charge transfers, then the mechanism, the mechanical mechanism, has to go again for a while in order to recharge the surface, and that gives me time to get away from the machine. So this is a Van de Graaff machine, and this device can place charge very efficiently on this upper spherical dome to get it up to a high charge and hence high voltage. And we can use it to demonstrate some fun things. And the first thing I'm going to demonstrate is just that I've got these small pith balls which have been coated with a metallic paint. And when I turn the voltage on, these are going to be repelled away from the surface of this sphere. So we'll watch that effect. And you'll notice that I am slightly afraid of the high charge that's going to be placed on the machine. And so I will use the stick to turn it on because I've been zapped before, and you'll notice I'll also keep my distance a little bit. Okay, so let's turn it on. And there is an adjustment knob here where we can turn up the belt speed. So I'm going to turn up the speed. And now what's taking place is charge is being taken off of the power supply. There's a brush attached to the supply and being carried up by the belt to the top sphere where a brush removes some of the charge and transfers it to the sphere. And as those pith balls come in contact with the sphere, they're picking up the same charge, the same type of charge, and then being repelled away from the surface. And so that's sort of like if you've ever seen a Van de Graaff machine where the hair of the experimenter stands on end. These are pith balls standing up on end as they're repelled from the sphere and from each other, so we can make them dance. Okay, so I am going to then demonstrate the next thing. And very carefully power this off. And now it'll hold its charge a little bit, so we see those pith balls still dancing, but gradually they lose their charge to the environment. And if I wanted to rapidly discharge, I've got a second sphere here which is attached to ground, so I can touch the sphere. And then we hear that crack, and the big sphere is discharged. But for now, I'm going to demonstrate the second effect, which is if I place a set of pie pans on top of the Van de Graaff machine, you might stop and think about what you expect to happen to those pie plates once I power things back up. Okay, so I'm going to power it back up and we'll see. Get the belt going again so it can transfer charge to the top sphere. That's called a flying saucer demonstration. And the reason for the effect is that all of the pie pans became light charged through contact with each other and with the dome. And when they're all light charged, then they all repel and they fly off in different directions. Okay, so now I'm going to talk about the lightning rod effect. which is that when we have a sharp point on an object, like this rod has a sharp point, it's an alligator clip extending from it, the electric field is going to be stronger at that sharp point than it would be at a more rounded surface. And my other object, these are both connected to the ground of the machine. My other object is going to be the rounded sphere that I've been using so far to discharge. And what I want to illustrate is the difference in behavior between these two objects based on whether or not they have that sharp point. So I'm going to turn things back on and dim the light so that you can see the sparks that are generated. Okay, so first I'm going to show the spark that occurs between this rounded sphere and the Van de Graaff. And hopefully you can see even the color of the light emitted. Maybe we'll dim the lights just a bit more. Oh yeah, now we can really see it. So, when the electric field between the two spheres builds up to greater than 3 million volts per meter, which we know is the breakdown electric field strength of air, then a spark is generated. And every time it discharges, the charge has to build up again on the Van de Graaff. So there's a delay between sparks. And if you're standing close, you can even begin to smell the ozone. And there's the crackling of the air as pressure differences are created as the charge makes its way through the air. So that's one demonstration with a rounded surface. And then I'm going to show the same demonstration. Let's discharge that for a second. With the alligator clip. So now I'm going to hold the alligator clip up close to the sphere. And this time, we don't see the sharp sparks coming at regular intervals. What we see is a continuous emission of charge from the Van de Graaff, and it's very hard to see. You may not be able to see it on the camera at all. If you listen closely, you'll hear a hiss. That hissing is the discharge to the alligator clip. Because it's a sharp point, it can much more readily build up to the electric field required to break down the air, which is 3 million volts per meter. If I do the sphere, sharp crackles, put in the alligator clip, which then acts as a lightning rod, is drawing charge off to it in preference to the big sphere. Then it's a more continuous emission of charge. So I'm going to turn things off. And today was a good day because there was no serious shocking of your instructor. All right, that's it for today.